Check. So in this video, I'm just gonna continue our next session, our earlier session. So in this video, I will learning about day 11 Jeremy's IT or CCNA 200 to 301, and I will be learning to configure and troubleshooting a static network in the lab, the Cisco packet trace. So first of all, we want to open the Jeremy's IT lab video. Okay, so this is on the troubleshooting static routes. We can download the lab here. So we search for day 11 troubleshooting. We have a long way to go. Day 63. So it's gonna be 1 or 2 months. And all of this. Name it to record it. Reload. Okay. We open. I want to setting my mic so you can hear clearly for my voice. Filter, and I think I'm gonna do some gain here. 19 dB. Gonna check it first so you clearly hear my voice. So you can clearly hear my voice. Maybe 20. Let's check the gain. That. So now I'm gonna open Cisco. So our job is to troubleshoot what is the trouble in here. Why PC1 and PC2 is not connected. So the trouble in here are in this Xbox. We can see PC1 and PC2 are unable to ping each other. So we can, and there is one misconfiguration on each router. Find and fix the misconfiguration. We have successfully completed the lab when PC1 and PC2 can ping each other. So as we can see, we have to troubleshoot at one lens too. At one lens first, I mean. So in this section, it's saying lah 192.168.1.0/24. So the PC1 must be 192.168.1.1, and router 1 G01 must be 192.168.1.254. You can see here config settings. The default gateway is right. The fast Ethernet 0 is right too. So there is no problem in PC1 configuration. So for the router one, can see our configuration in here. Okay, We put enable const terminal and do show run conf. Do show run. For the configuration in here, we can see IP address to router 2 is 12.1. Okay, next order. Refresh gigabit internet 0 1 gigabit internet 0 1 must be dot 254 54. Okay, there's no configuration. Do show IP interface brief. Again, 12.1 for the G00, 12.1 correct. 1254 G01 correct, and the status is up. Okay. There's no misconfiguration in that IP addressing. Now we can see our routing. To see the status of our routing IP route, we can type the syntax or command do show IP route. As we can see here, we have the static connection to 3.0/24. Yes, via 192.168.12.3. Via 192.168.12.3. As you can see, for the destination address 192.168.3.0/24, the next hop IP address is wrong here. We can see in here that it connected to 192.168.12.3. There was no 12.3 in here. So the correct one is 192.168.12.2. So for the exit interface, if you use exit interface, it will be exit interface from R1 G00. Okay, so we have to remove that IP route configuration. So to remove IP route configuration, we use no command. So no IP route 192.168.3.0.255.255.255.0 192.168.12.3. We have to remove that. Okay. Oh. We remove that no text, and we can add the correct configuration in this routing table. So you put 192.168.12.2. Okay, and we can check on do show IP route. The static route is already correct via U00 R2's U00. Okay. We can save the configuration and do right. Okay. And now we move in to R2. We have to check the IP address first on this interface. We go to command line, CLI, and come to show IP interface brief. And two. So for the gigabit Ethernet 00, the IP address is 12.2. 12.2, yes, okay. For the gigabit 01, it's 13.2. Okay. Yeah, it's good. There's no issue for the interface. And now we can see the IP route. To show IP route. For the static configuration, we can see here two of the configuration that made for the destination for each host for the 1.0/24 and 3.0/24. So for the 1.0/24, it is connected to via 12.1. Okay, that's correct. And for the 3.0/24, it uses the exit interface command. So for the 30, this one is directly connected to gigabit Ethernet 00. For the exit interface, this section is wrong, because for the exit interface, you have to set the static configuration for the exit interface for that device exit interface yet exit interface. I mean that exit interface, you have to set that, and it means the exit interface in the router 2 is G01. So we have to remove this configuration. So to remove the configuration, we use no command. No IP route 192.168.3.0 255.255.255.0 192.168 gig 00. We have to remove that configuration. Now we check if the static configuration is already removed. Do show IP route. So it removed. The C symbol is 1. The S symbol is 1. So we add the configuration once more. Control A. A. And we put gigabit gig 01 in that, replacing that G0. Okay. Default route without gateway. If not, point-to-point interface may impact performance. Don't worry about that. We can save the configuration, do right, and exit. Now we move into R2. First of all, we have to check the IP address first. For the G00, it will be 192.168.13.3. Enable, honesty, show, do, Show IP interface brief. For the gigabit internet 00, the IP is wrong. 23.3. It didn't match for the subnetting itself. And for the G01, it's correct. 3 to 25. So we have to configure this first. Before we remove that configuration from gigabit internet 00, we have to check that IP route is correct. So we do the command do show IP route. So for the static route itself, there is no configuration of static routing in here. So we also have to configure the static route. Okay. We go to interface. G00. Yes. G00. No IP address. 192.168. 23. Yeah. 23. 255. And the 23. The 3. 255.0. Have to remove the configuration and add the new IP address, the new correct IP address 30. Okay, and now we have to configure that static routes. So the command was IP route 192.168. So for the 192.168.3.0, it already directly connect for the host, for the end host in that local area. So our job is to route the, packets to the 192.168.1.0, 255.255.255.0 via as we can see here. So it means we have to put G01 interface for that exit interface. Then here I'm just gonna use the next hop IP. So 192.168.13.2. That's the correct IP route. We can check do show IP route. Okay, it is already connected via 17.2. And now we can check the PC's default route configuration. So default route is 2.254, right? And the IP address is 3.1. 255. Okay. So for my understanding, I'm already completely in troubleshoot this, and the final thoughts we have to check for the connection through the ping. I'm just gonna ping from PC1 to PC2. Ping 192.168.3.1. Ping here So it must be RTO, request timeout, request timeout, and request timeout, because for the first time, um, routing, it normally, wait, as you can see here, request timeout, request timeout, request timeout, and then the routing will be successful. You can ping again, and the ping will be successful, as you can see here. Okay, that's it for this lab. If you can understand, what can I understand? Let's get into another video. Gonna watch this
Welcome to
conclusion
Jeremy's
in
IT
here.
Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. You may recognize this network topology. This is the same network we configured in the previous lab. However, this time there are a few configuration errors, so PC1 and PC2 are unable to ping each other. As the lab instructions say, there is one misconfiguration per router, so we have to find and fix the misconfigurations. Troubleshooting labs like this are great practice for the CCNA. Troubleshooting helps.
It fails because the outgoing frame from R2's destination MAC is the same address for R1's G00. Outgoing frame from R2's, let's see, outgoing frame from R2's destination MAC. Okay, R2's destination MAC is G00 from R2. R2's is the same address for R1's G00. Okay, R drops the frame because the destination MAC doesn't match to why this happens. Just to check that the twin address are removed with no fixed one.
Test your knowledge of the concept, and troubleshooting questions may also appear on the CCNA exam. I highly recommend you try to complete this lab yourself first. If you watched the video before, you will already know what the problems in the network are, and won't practice your own troubleshooting skills. Okay, before we get started troubleshooting, we should confirm the problem. PC1 and PC2 are not able to ping each other. I'll go on PC1 and try to ping PC2. Okay, let's send that ping. Ping 192.168.3.1. Okay, the ping indeed does not work. IP config. Here you can see the IP address, subnet mask, and default gateway. If you want more detail, use the command ipconfig/all. This gives more information, such as the physical address. What is the physical address? Well, it's the MAC address. Okay, let's see if we can ping the default gateway. Since to reach other networks, we need to be able to reach the default gateway. In 192.168.1.254. Okay, no problems here. Let's go on our one net.
And I've had enough understanding for this troubleshooting. You know, what's type of here we go again.
Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to Chirp. This video, unlike the last one, is not going to be practical, meaning that most of the information will be across network. We'll cover the entire process of sending a packet to a remote destination. This will include things like ARP, encapsulation, de-encapsulation, etc. Of course, there are different levels of depth we can go into when talking about this process, and I won't give unnecessary details that only be expected of a CCNP or CCIE. But in this video, I hope to give you a solid understanding to get you ready for your CCNA. My hope is that this video will help you put all of the pieces together that we learned previously. So this is the life of a packet, the process a packet goes through when being sent to remote networks. Here's the network topology we'll use for this video. If you watched day 11's video, you should recognize this topology. It's the same one we used to demonstrate static routing. You'll follow a packet being sent from PC1 in the 192.168.1.0/24 network to PC4 in the 192.168.4.0/24 network. Let's assume we have pre-configured static routes on these devices so that the packet will follow the same path as in the static routing video. That is from PC1 to R1 to R4 and then PC4. This doesn't have to be the path. The path that goes via R3 instead of R2 is valid too. We'll stick to the same path as well. Now, since we're not just looking at layer 3 in this video, let me add MAC addresses for these devices. I'll use 1111 for PC1. Now, as you know, a MAC address is actually 12 hexadecimal characters. But just to save space, I'll shorten them to 4. R1's G02 interface has a MAC address of AAAA, and its G00 interface has a MAC address of BBB. That's something I didn't mention before. Each interface on a network device has a unique MAC address. Note that switch 1's interface also have MAC addresses. However, for this video, it's not necessary to know the MAC addresses of the switches. So to avoid clutter, I'll leave them out of this diagram. R2 has a MAC address of CCCC on its G00 interface and DDDD on its G01 interface. R4 has a MAC address of EEEE on its G01 interface and FFFE on its G02 interface. I didn't make it all Fs because the MAC address of FFFF, 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 12 Fs, is the broadcast MAC address. So just to avoid confusion, I added that E on the end. Finally, PC4 has a MAC address of 4444. Okay, so PC1 wants to send some data to PC4, and it's encapsulated in this IP header. The source is 192.168.1.1, PC1's IP address, and the destination is 192.168.4.1, PC4's IP address. Now, because PC1's IP address is in the 192.168.1.0/24 network, it notices that the address 192.168.4.1 is in a different network. So it knows that it needs to send the packet to its default gateway, which is R1, something we have already pre-configured. However, in this example, PC1 has not sent any traffic yet, so it needs to use ARP, the address resolution protocol, something we covered in a previous video. Let's look at the ARP process. So, PC1 makes this ARP request packet. The source IP is its own IP address, and the destination is R1's G02 interface, which is the default gateway.
Okay. So for my understanding here, so when the first time that you send the packet, after you configure all the configuration just like we do in our last configuration, and when we ping the PC2, it will be RTO or request time. So in this first time, yes. So for the first time identifying all of the interface, the source and the destination, the PC will be sending the ARP request for the first time. Just remember, for the first time. So the ARP request in the PC1 is sending is source IP, it's his IP, and the destination IP is for the default gateway that was set in that interface. And the for destination MAC address, it's the destination broadcast F, the trace of 4 Fs you can see in the screen. And for the source MAC address, it's source MAC address 111.
Gateway configured on PC once more. Predict is in a different network. What knows that needs to send the packet to its default gateway, which is R1, something we have already pre-configured. However, in this example, PC1 has not sent any traffic yet, so it needs to use ARP, address resolution protocol, something we covered in a previous video. Let's look at the ARP. So, PC1 makes this ARP request packet. The source IP is its own IP address, and the destination is R1's G02 interface, which is the default gateway configured on PC1. Next is the MAC address. This is a minor point, but note that I put the source IP before the destination MAC, but the destination MAC before the source MAC. That's because in the IPv4 header, IP address comes first. In the Ethernet header, the destination MAC address. Anyway, just a minor point. The destination MAC address is the broadcast MAC address of all Fs, because it doesn't know the MAC address of R1. It will send the frame to all hosts on the network. Finally, the source MAC address is its own MAC address. So, it sends the frame, which switch 1 receives and broadcasts out of all its interfaces, except the one it received the frame. In this example, and R1 are connected to switch 1. That means that switch 1 will forward the frame out of its G00 interface. To translate the meaning of this frame into English, PC1 is basically saying, hi, 193.168.1.254. What's your MAC address? Although I'm not going to really talk about the switches much in the video, note that switch 1 learns PC1's MAC address on its G01 interface when the frame arrives on G01. That's your MAC address. Although I'm not going to really talk about the switches much in the video, note that switch 1 learns PC1's MAC address on its G01 interface when the frame arrives on. When this broadcast frame arrives in R1, it notices that the destination IP is its own IP, so it creates this ARP reply frame to send back to PC1. Although the ARP request message was broadcast in this phase, note that switch 1 learns PC1's MAC address on its G01 interface when the frame arrives on G01. When this broadcast frame arrives in R1, it notices that the destination IP is its own IP, So it creates this ARP reply frame sent back to PC1. Although the ARP request message was broadcast, because R1 learned PC1's IP and MAC addresses from the ARP request message.
So for the up request and up reply, it's basically for the fresher. So when you finishing the configuration and you try to ping or connect with other networks, it will be sending that ARP request. And for the ARP request is the broadcast. So for the broadcast, it floats out of the network, and when it reaches the destination for that ARP request, the ARP reply will be unicast. And as you can see for this picture, the PC1 will send that ARP request for the broadcast, and R1 receive that packet because it match with the source destination IP address from PC1 and 192.168.1.254. It's the IP of G02 R1s. So the R1 will be replying that as a unicast. So it will not be floated again or broadcast to another sets of network.
Message. The ARP reply can be sent unicast directly to PC1. So that's what R1 does. To translate this ARP reply message into English, basically it means, hi 192.168.1.1. This is 192.168.1.254. MAC addresses AAAA. Note that switch 1 will learn R1's MAC address from this message. Train arrives on its G00 interface. So now PC1 knows the MAC address of its default gateway, so it encapsulates the packet with its Ethernet header. Keep in mind, the original packet is not changed. The destination address will be PC4's IP address, not R1's IP address. Only at layer 2 is the destination set to R1. Sends the frame to R1. Receives it and removes the Ethernet link to R1. So, sends the frame to R1. R1 receives it and removes the Ethernet header. It looks up the destination in its routing table. The most specific match is this entry for the 192.
For the discoveries that start with end hosts like PCs, or you want to ping from the PC1 to another network, another subnet, and not in that local area network or that network, the first thing that will occur will be the ARP request and ARP reply. So the ARP request is broadcast and ARP reply will be unicast. So after the R1 will be replying that ARP reply, the PC1 will know the IP and the MAC address of R1. So it will be sending the Ethernet header and it will be sending the IPv4 header, and it will be removed and encapsulate Ethernet header. And when it reaches to R1, so for the R1 will be communicating with other network device. I mean, it will be communicating with layer 3 or layer network devices, and it will be seeing the routing table. Okay.
168.4.0/24 network, which specifies the next hop of 192.168.12.2. So, R1 will have to encapsulate this packet with an Ethernet frame with the appropriate MAC address for 192.168.12.2. However, R1 doesn't know R2's MAC address. So, how will it learn R2's MAC address?
ARP request.
It will use ARP. The source IP address of this ARP request will be R1's, and the destination will be R2's. Destination MAC address is all X, the broadcast MAC, because R1 doesn't know R2's MAC address. And the source is BBBB, which is the MAC address of R1's G00. So, it sends the ARP request, and R2 receives it. Basically, what this ARP request says is, I want to say to their MAC address. R2 receives the broadcast, and since the destination IP address matches its own IP address, it makes this ARP reply to send to R1. Once again, because it learned the IP and MAC addresses of R1 from the ARP request, it doesn't have to broadcast. So it sends this ARP reply. Basically says, hi, 192.168.12.1. This is 192.168.12.2. MAC address is CCCC. Okay, now
For this section, I'm thinking that for the Ethernet header, I mean, for this section, you didn't have to how do you know that destination IP address for that second interface? I mean for the ARP request, you can see here source IP, it's G00R1's IP. You can see here 192.168.12.1. It's the R1 G00 interface. For destination IP, how do you know that? Or because it 1 second, so we didn't have to broadcast this destination IP. So for the ARP request, I think from a personal opinion, so the simple is the ARP request will be the ARP request useful for finding destination MAC address, just for the search of the destination MAC address. As you can see, the all F's. The main purpose of the ARP request and ARP reply is to find that device MAC address. I mean, to find that interface MAC address. As the Jeremy's saying earlier, each interface have their unique MAC address. So it's not like one device is one MAC address. No, the router, switch, and other device. When you get another port, it has that unique MAC address. So for the ARP request, I had a conclusion that it was it is useful for just um I mean finding that MAC address
What
for
this ARP
your
request says is, hi, 192.168.12.2,
another interface.
their MAC address. ARP2 receives the broadcast, and since the destination IP address matches its own IP address,
I'm just gonna first and ask for the easy ARP request and ARP main for this to this over um only here for the yes, discovering the MAC address of device on a local network and you not only know its IP address is the primary purpose of ARP request and ARP privacy. This is a quick breakdown of how process works. ARP request device broadcast message to the entire local network asking who has this IP address? Tell me your MAC address. Right? The device assigned to that IP address respond directly unicast requester stating that IP address belongs to me and here is my MAC address. A trivial hidden benefit. While discovering the target MAC address is the main goal, the ARP process has an equally important secondary purpose, updating the sender ARP cache. When the requester sends ARP request, it also includes its own IP and MAC address. Because of this, every device that receives the broadcast, or including that final target, currently learns that the sender IP to MAC mapping and save it to their local memory for future communication. Got it.
it makes this ARP reply to send to R1. Once again, because it learned the IP and MAC addresses of R1 from the ARP request, it doesn't have to broadcast them.
That's
So it sends this ARP reply back. Basically says, hi, 192.168.12.1. This is 192.168.12.2. MAC address is CCCC. Okay, now R1 knows R2's MAC address, so it can encapsulate the packet with an Ethernet header, inserting R2's MAC address in the destination field and the MAC address of R1's G00 interface in the source field. Sends it to R2. After receiving the frame, R2 removes the Ethernet header. R2 then looks up the destination IP address in its routing table, and the most specific match is this one for 192.168.4.0/24, with the next hop of 2.168.24.4. Although 192.168.24.0/24 is a connected network to R2, it doesn't know the MAC address of 4. So, you know what's next. R2
R2 will be sending the ARP request and then R4 will be replying that as a unicast because it matched that source destination IP and it will be sending the MAC address into the R2's ARP table, and then R2 will be encapsulating the data and R4 will be receiving that data.
We'll use ARP to discover R4's MAC address. R2 prepares this ARP request frame using its own IP and MAC addresses for the source, R4's IP address of the destination, broadcast MAC address, and it forwards it out of its G01 interface. With this ARP request, R2 is saying that when the 2.4 R4 receives the broadcast, and since the destination IP address is its own, it creates this ARP reply frame to send back to R2. Once again, it already knows R2's IP and MAC address because they were used as the source addresses for the ARP request. It sends the unicast frame back to R2. With this ARP reply, R4 is saying, "Hi, 192.168.24.2. This is 192.168.24.4. My MAC address is EEEE." Now that R2 knows R4's MAC address, it encapsulates PC1's packet with an Ethernet header with a destination MAC address of EEEE, which is R4's G01 interface, and a source MAC address of DDDD, which is R2's G01 interface. R4 receives the frame and removes the Ethernet header. It looks up 192.168.4.1 in its routing table, and the most specific match is this entry for 192.168.4.0/24, which is directly connected via the G02 interface. But once again, R4 doesn't know PC4's MAC address. You know what it has to do next. It will use ARP to learn PC4's MAC address. It prepares this ARP request frame. Again, the source IP and MAC addresses are its own, the destination IP address is PC4's, and the destination MAC is the broadcast MAC address of all addresses. It sends this message out of its G02 interface saying, "Hi, 192.168.4.1 with your MAC address." Note that switch 4 will learn R4's MAC address on the G00 interface from the source MAC address field of this Ethernet frame. After PC4 receives the frame, it checks the destination IP address. Since it is its own IP address, it will send an ARP reply. The ARP reply will be unicast, using PC4's IP and MAC addresses for the source, and R4's IP and MAC addresses for the destination. It sends the frame out of its network interface. Hi, 192.168.4.254. This is 192.168.4.1. MAC address is 4444. Note that switch 4 learns PC4's MAC address when it arrives on its G01 interface. Now that R4 knows PC4's MAC address, it adds an Ethernet header to the packet using its own MAC address on the G02 interface as the source address, and PC4's MAC address as the destination. R4 sends the frame to PC4. Finally, it has reached its destination. Notice that the original packet hasn't changed throughout the process. It's always used the same IP header with a source IP address of 192.168.1.1 and a destination IP address of 192.168.4.1. Also, notice that the switches didn't actually modify the frames at any point. The switches forwarded the frames and learned the MAC addresses, but they don't actually de-encapsulate and then re-encapsulate the packet with the new Ethernet header. Okay, and it is the address of 192.168.1.1 and the destination IP address of 192.168.4.1. Also, notice that the switches didn't actually modify the frames at any point. The switches forwarded the frames and learned the MAC addresses, but they don't actually de-encapsulate and then re-encapsulate the packet with a new Ethernet header. Okay, now let's say PC4 sends a reply back to PC1, and we've configured static routes on the routers that the traffic follows the same path on the way back to PC1, going via switch 4, R4, R2, R1, switch 1, and then reaching PC1. What will be different? First off, there will be one major difference. Since these devices have already gone through the ARP process, there won't be any need for ARP requests and replies. The packet will simply be forwarded from device to device, being de-encapsulated and then re-encapsulated It is received by and then forwarded by each router. So, that's it. Just a basic walkthrough of how a packet is forwarded between routers to pass it along to its final destination. Now, as for today's quiz, I'll do something different than usual. Instead of having multiple choice questions as usual, we'll use this same diagram to test your understanding. Let's get started with the quiz. Here's question 1. PC4 sends a packet to PC1. What is the destination MAC address when it is sent from PC4's network interface?
What is the destination MAC address when it is sent from PC4's network interfaces? Okay. For the destination MAC address, it will be destination of R4's G02 FFFE. That's the destination MAC address from the Ethernet header.
Pause the video to think about your answer. The answer is FFFE, which is the MAC address of R4's G02 interface. That's because to send a packet to PC1, which is in a remote network, R4 must send the packet to its default gateway, R4. To do that, it encapsulates the packet with an Ethernet header with its default gateway's MAC address, destination, to its default gateway, our remote network. R4 must send the packet to its default gateway, R4. To do that, it encapsulates the packet with an Ethernet header.
Okay. Is encapsulate packet with Ethernet header
with its default gateway's MAC address and the destination. Okay, let's go to question 2.
Encaps.
4 sends a packet to PC1. What is the source MAC address when it is received on R1's G00 interface?
PC1 sends a packet to PC1. What's the source MAC address when it is received? R1's G00 interface. R1 G00 interface. What is the source MAC address when it is received? Source 4 to 1 receive. It means that destination is BBBB. So for the source is R2 R2's G00 MAC address. So it's CCCC.
Pause the video to think about your answer. The answer is CCCC, which is the MAC address of R2's G00 interface. When R2 sends the packet to R1 en route to its destination, PC1, it encapsulates the packet with an Ethernet header using its own MAC address as the source MAC address. Okay, let's go to question 3. PC4 sends a packet to PC1. What is the source MAC address when it is sent from switch 1's G01 interface?
PC4 sends a packet to PC1. What is the source MAC address when it is sent from switch 1's G01 interface? Switch 1? Which one? G01 interface. Where's the source MAC address? Source MAC address is A.
Pause the video to think about your answer.
Because R1s will be encapsulate data from that ARP table that it gets from the first time discoveries, and it will be encapsulated the data and adds the Ethernet header for the source and the source MAC address from it will be forward from which one? G01 interface will be the MAC address of R1's G02 is AAAA.
The answer is AAAA,
Yeah.
which is the MAC address of R1's G02 interface. Which one doesn't alter the frame to use its own MAC address? It simply forwards the frame out of the correct interface, or floods it if it doesn't know the destination. Let's go to question 4. PC4 sends a packet to PC1. What is the destination IP address when it is sent from R4's G01 interface?
PC4 sends a packet to PC1. What is the destination IP address when it is sent from R4's G01 into R4's G01 interface? What is the destination IP address? Port 1. Destination IP address. For the destination address when it's R01 into, I think for my knowledge about this.
Gaming banget gini nggak sekarang?
Kayak
Hah?
biasa. Bener tuh.
Cepet-cepet.
Yuk, jadi bang.
Besok datang saat. Datang. Ya.
What is the destination IP address when it is sent from R4's G01 base? For the destination IP address is the same. It is different from the ARP request and ARP reply that has that many MAC address hop to another device.
Tahu.
So it differs from another interface. So in my opinion, so it's gonna be the PC1 IP address. So the answer is 192.168.1.1.
Pause the video to think about your answer. The answer is 192.168.1.1, which is the IP address of PC1. Although each router modifies the source and destination MAC addresses in the Ethernet header as it forwards the packet, they don't modify the original packet itself, so the destination IP address won't change. Since PC4 is sending the packet to PC1, that means the destination will be PC1's IP address, 192.168.1.1. Let's go to question 5. PC4 sends a packet to PC1. What is the source IP address when it is received on R1's G00 interface?
PC4 sends a packet to PC1. What is the source IP address when it receives R1's G01 G00 interface? So for the source IP address, it will be the same as the original IP address. As the last question.
Pause the video to think about
So
your
the
answer.
source is 192.168.4.1.
The answer is 192.168.4.1, which is the IP address of PC4. As I said in the last question, the original packet is not modified as the routers forward it to its destination. So through the whole route, source IP address remains PC4's IP address, 192.168.4.1. Okay, for this video, there will once again be supplementary materials to help you practice what you've learned. There will be a packet tracer practice lab, in which you use packet tracer's simulation mode to analyze packet and test your knowledge and that will be the next video. And that's it. There won't be Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and comment and share the video to help spread this free series of videos. Thanks for your help. Also, remember to download this Packet Tracer Practice Lab, link in the description. This lab will be a little different. You won't actually
So in this lab, I will test my understanding about this life of a packet video from the last video. So that we will be identifying all the ARP requests and all the ARP reply as you sending the packet, and then we have to identify um so for the source instructions, PC1 pings PC4. Identify the source or destination MAC address at each specified point in the route to PC. Identify the MAC address by device and interface. So the MAC of R1's P00. Source or destination MAC at PC1 to which one segment.
to be doing any configuration. However, you will be testing your knowledge of what was covered in Day 12's lecture video in a hands-on environment. This is essential knowledge. Have a basic understanding of how a packet travels from source to destination. So, there are three main questions: 1, 2, and 3. You're asked to identify the source and destination MAC addresses used. It travels between different points in. Let's get right on it with question 1. Question 1 says, PC1 pings PC4. Okay, PC1 is here in the 192.168.1.0/24 network. PC4 is in the 192.168.3.0. We are asked to identify the source and destination MAC addresses at each specified point in the route to PC4. Just an aside, remember that the source and destination IP addresses will never change. The source will be PC1's IP address of 192.168.1.1, and the destination will be PC4's IP address of 192.168.3.1. we are told to identify the MAC address by identifying the device and interface. To avoid clutter, I didn't write out all of the MAC addresses for each device and interface. So we'll just say R1G00 for it, instead of the whole MAC address. I'll then show you the CLI command to verify your answer. Okay, so part A of question 1 asks the source and destination MAC addresses, the connection segment between PC1 and switch 1. Well, let's think about this. Because PC4 is located on a different network, PC1 will encapsulate the packet with an Ethernet header, and the destination MAC address will be the MAC address of its default gateway. In this case, that is R1's G00 interface. So that will be the destination MAC address. How about the source? Well, that will be PC1's MAC address, since it just sent the frame. How about B, the source and destination MAC at the switch 1 to R1 segment? Well, it should be the same as in A. Switch 1 won't actually change the source and destination MAC addresses in the frame. It will simply use the source MAC address field in the Ethernet header to learn PC1's MAC address if it doesn't already know it, and then forward the frame to the proper destination, or flood it if it hasn't learned the destination MAC address. So, let's confirm these first two answers using the CLI and packet tracer simulation. First, though, I'll send a ping from PC1 to PC4 just to allow the ARP and MAC learning processes to complete. We can just view the ping packet in simulation mode. I'll hop on PC1. So enter the CLI of PC1, and let's ping PC4. Ping 192.168.3.1. You'll notice that when you first issue the ping command, not all of them are successful. This is because all of these devices have to finish their ARP process, and the pings time out while. Also note that in a Windows PC, when you use the ping command, by default, 4 pings are active. Now let's send another ping. Hit the up arrow to repeat the command, enter it, and there you go. All pings are now successful. Now let's also check the MAC addresses of PC1, R1's G00 interface first. On a Windows PC, use this command, ipconfig/all. Scroll up here for the Fast Ethernet 0 interface, and check the physical address here, which is the MAC address. Okay, let's just remember these last 4 digits. So PC1 is 1111. How about R1? Let's check. I'll hop on R1. Enter privileged exec mode with enable, and you can view the MAC address of the interface with this command. Show interface G00. Scroll up here, and it says hardware is gigabit Ethernet. Address is 000001AA AAAA. Again, let's remember those last 4 digits. R1's G00 interface is AAAA. However, let me point out one more thing. Next to this MAC address, it says BIA, followed by a different address. I said in one of my lecture videos that BIA, or burned-in address, is another word for MAC address. So what's up? Does this interface have 2 different MAC addresses? Well, the burned-in address is the actual MAC address assigned to the interface by the device maker, in this case Cisco, when it was made. However, you can actually configure a different MAC address in the CLI, and it will use that one. That's what I did in this case, to make it easier to remember. Let's check out that command to configure the MAC address. Show running config. Scroll down to gigabit Ethernet 00, and there it is. MAC-address, followed by the MAC address you want to configure. Okay, so the last 4 digits of PC1's MAC address are 1111, and for R1, they're AAAA. Now let's actually confirm by using simulation mode. Click on simulation mode in the bottom right here. Then let's go to PC1 again, and send that ping once more. 192.168.3.1. Here's the ICMP packet. And I'll hit this arrow once, so it is sent to switch 1. Let's check the source and destination by clicking here to analyze it. Look at the in layer. This is the frame as it is received by switch 1. Layer 2, Ethernet header is from 1111, which is PC1, to AAAA, which is R1's G00 interface, just like we said. Notice the layer 1 info here too, showing the physical interface it was received on. Now on the right here, out layers, is the frame as it is sent from switch 1 to R1. Notice the layer 2 info is the same, from 1111 to AAAA. And you can see gigabit Ethernet 01 in the layer 1 info, as it will exit out of the G01 interface route to R1. So that's A and B. I'll close this here, and I'll just press this once more so it is sent to R1. Let's move on to C. What are the source and destination MAC addresses at the R1 to R2 segment? Although the source and destination IP addresses will remain the same, as R1 encapsulates the packet with an Ethernet header, it will use the MAC address of its G01 interface as the source, and the MAC address of R2's G00 interface, which is the next hop in the route, as the destination. Let's check their MAC addresses to be sure. I'll hop on R1 once. Show interface G01. Okay, the last 4 digits are BBBB. Now let's check on R2. Enter privileged exec mode with enable. Next, show interface G00. Okay, the last 4 digits are CCCC. So the source should be BBBB and the destination CCCC. Let's check. The packet is here at R1 now. I'll click on it. Let's check the right side, out layers, which is the packet as it is forwarded out of R1's G01 interface. You can see the source MAC of BBBB and the destination MAC of CCCC. Perfect. Okay, I'll exit out of here. Click this arrow once more to send the packet to R2. Okay, now here the explanation is similar to the last step, so let's just skim through. The source should be the MAC address of R2's G01 interface, and the destination should be the MAC address of R3's G00 interface. Let's go back to the CLI of R2 to check the MAC address. Show interface G01. Okay, last 4 digits are DDDD. Now let's go to the CLI of R2. Enter privileged exec mode with enable. Next, show interface G00. Last 4 digits are EEE. Okay, let's check our answer. Click on the frame here, and again, let's look at the out layers. You can see the source of DDDD and destination of EEEE, just like we predicted. I'll exit this frame here, and then click the arrow again to send it to R3. Next, how about E, the source and destination MAC between R3 and switch 2? Well, at this point, the destination IP address is part of a network connected to R3, 192.168.3.0/24. So R3 knows it can send the packet directly to PC4. So it will set the destination MAC address to PC4's MAC address and use its own address as the source. So actually, the answers should be the same for part E and F of this question. So I'll send the packet forward once more, so we can check the in and out sections at switch 2. Okay, let's check the MAC address. I'll go back to the CLI of R3. Let's check G01's MAC. Show interface G01. Okay, the last 4 digits are FFFF. How about PC4? Let's click on PC4, click on desktop, and prompt. And do you remember the command? It's ipconfig/all. Scroll up to the fast Ethernet 0 interface, and here's the physical address, the MAC address. Last four digits are 4444. Okay, so for both E and F, the source should be the MAC address ending with FFFF, and the destination should be the MAC address ending with 4444. Let's click on that packet here. And notice that in both the in layers, which is the frame as it is received on P01, and the out layers, the frame as it is forwarded to P4, the source MAC ends with FFFF, destination MAC ends with 4444. So we were correct. So that's all for question 1. I'll exit simulation mode for now. Question 2 is shorter, involving a ping from PC1 to PC3, which is on the same network. The big difference here is that since the destination is on the same network as the source, PC1 won't send the packet to its default gateway. It will send it directly to the destination, PC3. Also, although switch 1 is in the middle, remember, it won't change the source or destination MAC addresses. It will simply forward the frame to its destination. So both A and B should have the same answer. The source should be PC1's MAC, which, if you remember, is 1111, and the destination should be PC3's MAC. Let's quickly check PC3's MAC. I'll go on the CLI of PC3, and now let's use that command once more. Remember, this is a command for Windows PCs. ipconfig-all. Scroll up to the fast Ethernet 0 interface, and here's the MAC address. Last four digits are 3333. Okay, before checking, ping from PC1 to PC2 just in case, so that the ARP and MAC learning process is complete. Ping 192.168.1.3. Okay, now let's go into simulation mode. Ping once more. Click on simulation mode in the bottom right. Return to PC1, and let's ping 192.168.1.3. I'll click the arrow once to forward the packet to switch 1. Let's check it. As you can see, as the packet comes into switch 1 via F01, and as it exits via F03, source MAC is PC1's, ending with 111, and the destination MAC is PC3's, ending with 3333. Okay, that's all for question 2. Now, for question 3, I want you to post your answers in the comment section of this video. I will leave a pinned comment down below with the question, but it will be in the same format as for question 1, but in reverse order. Leave your answers by identifying the device and interface. For example, the MAC address of R1's G01. You don't need to enter the actual MAC address of the interface. Okay, looking forward to your answer.
So for the question 3, PC4 pings PC1. The source MAC address is the source MAC address of PC4, and the destination MAC address is destination MAC address at the T01 R3. It's the same for the switch 1 segment and R3 segment. So for the source MAC address, it's source MAC address from R3 G00, and the destination MAC address is R2's G01. It's for the R3 to R2 segment, and from R2 to R1, the source MAC address will be G00R2 MAC address. The destination MAC address will be G01 R1's MAC address. And for the R1, the switch 1 and R1 switch 1 to PC1 will be the same. The source MAC address will be from R1's G00 and the destination will be the PC1 MAC address. But FFF satu ke satu, okay.
All for this lab.
I think that's all for this learning. For today, I'll see you.